Today we're going to cover Chapter 27 on electromagnetic induction. Electromagnetic induction is a really important area in physics because it's the physics behind how we generate electricity. So we know that an electric current produces a magnetic field. We've said that if we've got a long straight wire, if we're some distance away from the wire R, the magnetic field created by that current carrying wire is just mu naught I divided by 2 pi R. Now, if we actually want to make an electromagnet, generally what we do is we put a coil of wire together, such as a solenoid. And remember, we saw that the magnetic field inside a solenoid is equal to mu naught N times I, where N is the number of turns per length. So that's how we make an electromagnet. So we know currents create magnetic fields. The question is, can a magnetic field produce a current? Can we go the other way? And that question was answered back in the 1800s, both by Joseph Henry and by Michael Faraday. And we're going to see the importance of that as we go through the chapter. So here is some pictures of basically what Faraday did. And a galvanometer, by the way, is simply a device that measures a small current. So it's essentially like an ammeter, but measures very small currents. Here's what Faraday found. He found that if he moved a magnet near a coil of wire, then he induced a current in the circuit. So again, notice there's no battery or anything in here. Just moving a magnet in and out of a coil of wire created a current, and therefore there must be a voltage that's being created in the circuit. It's like there's a battery in there, but there's no battery. A couple important things to notice. When you push the magnet towards or into the coil, he got a current in one direction. When he pulled it back, he got a current in the other direction. Also, if you just hold a magnet stationary by a coil of wire, nothing happens. You don't get a current unless there's a change in the magnetic field going through the coil. Here's another version of one of the experiments that Faraday did. And here you'll notice that we have a galvanometer connected to a coil. And here we have a battery and a switch and another coil. The important thing to understand about this diagram is there is no electrical connection between that coil and that coil. So this is insulated wire. Notice, though, that both coils are wrapped around this piece of iron. This device, by the way, with two different coils that are not connected electrically, wrapped around iron, that is a transformer. And we'll talk more about that in our next online class. So here's the question. What do you think happens when we close the switch here? Do we get a current in the galvanometer? Well, the answer is that we only get a current right when the switch is either being opened or closed. If the switch is just closed constantly, then we do not get a reading in the galvanometer. Now, if you think about what we learned on the last slide, that should make sense to you. We know that when you close this switch, we're putting a current through this coil, and that generates a magnetic field. However, once the switch has been closed for more than a moment, the magnetic field being created by this coil is constant. That magnetic field is directed through this coil because of the iron. Magnetic fields like to stay in iron. But if the magnetic field created by this coil isn't changing, then there's not a changing magnetic field through this coil, and so we don't get a current. However, right when we close the switch, notice we're going from no magnetic field being created here to having a magnetic field. So we've got an increase in magnetic field here through that coil, and that's what creates a current. And so what we find is only when we're either closing the switch or opening the switch do we get a reading on our galvanometer. By the way, this is an important fact. Remember, if I have a constant current going through this coil, nothing happens in this coil. And we're going to see why that's important in the next chapter. Okay, so what did Faraday conclude from these types of experiments? Basically, what he concluded is that you get an induced current, and therefore, remember, it's voltages that create currents. So you get a voltage as long as you have a changing magnetic field through a coil, okay? And the voltage or EMF that's produced is proportional to the strength of the field, the size of the coil, and the rate of change. So if you move that magnet in and out faster, you get a greater voltage. If you have a stronger magnet, you get a greater voltage, etc. Okay, so obviously we want to put this into mathematical form, but before we can do that, we have to review the concept of magnetic flux. Let's remember what we mean by electric flux. Remember that electric flux, which we saw in Gauss's law, is defined as the integral of the electric field over the area. And if the electric field is constant over the area, remember that's simplified to the dot product of the electric field times the area. Remember, by the way, that the direction of the area is that surface area vector that's perpendicular to the surface. And so as we talked about when we first introduced this concept of flux, if the magnetic field, or in that case we're talking about the electric field, is in the same direction as the surface area vector, that's when we get the biggest flux. If it's perpendicular, we don't get any flux at all. And so we define magnetic flux in exactly the same way. Again, think of flux like flow. How much magnetic field is flowing through the area? If theta is equal to 0, that's when we get the maximum flux. By the way, remember, we saw this briefly when we looked at Gauss's law for magnetism. Okay, so again, if the magnetic flux is constant over the area, we get the same simplification as we got for electric flux. The units of magnetic flux. If you look at the formula, you'll notice that we have the unit of magnetic field, which is Tesla's, the unit of area, which is meters squared, and so it's Tesla's meters squared. Unlike for electric flux, where we don't define a unit, here we do. We define the Weber, and a Weber is a Tesla meter squared. Okay, so now that we have the concept of magnetic flux down, we can look at the definition of Faraday's law. So here is Faraday's law of induction. It says that the induced EMF, remember this is a voltage, an induced EMF, is proportional to the number of turns in the loop times the rate of change of the magnetic flux. And again, for all the problems we're going to do, the flux is going to be, or the magnetic field is going to be constant over the area, so that the flux is just BA cosine theta. Okay? So notice that the only time we get an induced voltage is if the magnetic field is changing, the area is changing, or the angle between them is changing. One of those things has to be changing, otherwise we don't get an induced voltage. By the way, often we're going to just talk about the average induced voltage, and in that case, we're going to use deltas instead of derivatives. Now, one of the things you'll notice about both of these formulas is that there is a minus sign in them. And that minus sign actually has a law of its own. And this is the significance of those minus signs. And we call it Lenz's law. An induced EMF is always in a direction that opposes the original change in flux that caused it. That's really important because think about this idea. I've got a coil and I take a magnetic field, I take a magnet and I push it towards the coil. That's going to induce a current in that coil. But what if that current turned this coil into a magnet where this end was the South Pole and this end was the North Pole? Well, that would mean that if you just moved a magnet a little bit towards a coil, the coil would then suck the magnet in. We'd be getting energy for nothing. That would violate conservation of energy. In fact, the opposite is true. When we push a north pole towards, into a solenoid, the solenoid will set up a magnetic field that opposes that. So as you push the magnet in, the current that's generated sets up a magnetic field that opposes the change you're trying to make. And that makes sense because we are generating electrical energy that's got to come from somewhere. Well, it's because we have to do work to move the magnet. Let's look at a number of examples using Lenz's law. So again, we know that the flux is equal to BA cosine theta. And what we've said is that in order to get an induced voltage, we have to have a change in flux. The flux has to be changing in time in some way. So here, if we take a north pole and we push it towards a coil, what we know is that the coil is going to set up a magnetic field to oppose the change. So in other words, if I push a north pole towards a coil, it wants to make a north pole. Here we're going to use right-hand rule number 3. So the coil wants to make a magnetic field pointing out of the screen to oppose this change. And so notice, put your thumb so it's pointing towards you. Notice that your fingers are going in the counterclockwise direction. And so the induced current would be counterclockwise. Let's look at another example. What if we have a coil and we move a magnetic field towards it from the side? So again, we're increasing the magnetic field in this direction as we bring that closer to the coil. In this particular case, though, there would be no induced current. And the reason for that is, remember that this theta is important. The surface area vector would be straight out in this case. Notice that if the magnetic field is to the right, there is no flux going through that loop. So there's no change in flux. In other words, theta is 90 degrees, and therefore the cosine of theta is 0. Let's look at some more examples. These problems are a little bit hard to understand when you first learn them. I always like to say, you want to be the loop. And here's what I mean by that. Loops don't like change. So in this case, let's look at the first example. We've got a magnetic field only in this region of space pointing straight out. And what we're doing with our loop is we are moving it to the right. So in other words, between this being our initial time, if we look a little bit later, here is the position of our loop. Notice that there is less magnetic field coming out of the loop now than there was before. If we've reduced the amount of magnetic field coming out, then the loop wants to make magnetic field to replace that. So in other words, the loop wants to make magnetic field pointing out. So put your thumb straight out. Notice what direction your fingers curl. They curl in a counterclockwise fashion. And so the induced current would be counterclockwise. Now notice, what if instead I had started with the loop out here and I moved it this way? Well, now all of a sudden there's more and more magnetic field coming out through the loop. So in that case, the loop would want to make clockwise current. In other words, it would want to make magnetic field in. So the loop will always do the opposite thing. The current generated will always oppose the change you're making. Let's look at another example. Here we have a loop that is shrinking. So it's going from this original size down to this size. So notice that as that loop gets smaller, there is less magnetic field going in. Well, when you're taking magnetic field away, the loop wants to make magnetic field in the same direction. So put your thumb towards the screen and look at the way your fingers are curling. They are curling in a clockwise direction. And so the induced current would be clockwise. Again, if we reverse the process, if the loop goes from smaller to bigger, then we would get a counterclockwise current, because now, since there's more and more magnetic field going in, the loop would want to make magnetic field coming out. Let's look at this one. We've got a magnetic field going to the left, and the loop is rotating, and we're told that this side is coming out. So this side is coming out, and this side is going in. If you think about what's going on here, as that loop starts to spin, there's more and more magnetic field going into the loop. Therefore, the loop wants to make magnetic field coming out. So you'd put your thumb in the outward direction. Your fingers would curl in a counterclockwise direction. And so the answer is counterclockwise. Let's look at a problem similar to the kind of problem that I would expect you to be able to do for the final. Here we have a circular coil of radius 2 centimeters, contains 200 loops, and it's perpendicular to a uniform magnetic field of 0.5 teslas. We're then told that the magnetic field increases to 1.75 teslas in 0.15 seconds, and we want to know the magnitude of the induced EMF. And we also want to know the direction of the induced current. Let's do that part first. So notice that we have more and more magnetic field going into the loop. If we're increasing the magnetic field going into the loop wants to make a magnetic field in the opposite direction. So put your thumb coming out of the screen towards you. Notice that your fingers curl in a counterclockwise direction. Okay, so that's the direction of the induced current. We now want to figure out the magnitude of the EMF. So in order to do this, we're going to use the fact that the average induced EMF is going to be minus n delta phi over delta t, where phi is the magnetic flux, Ba cosine theta. And notice really all we're doing here is trying to figure out what of the flux is changing. If nothing's changing, there's no induced current, no induced voltage. Also, notice here that we want the magnitude. So I'm just going to take the absolute value of this. So I've got the absolute value of negative n. N is just the number of loops. But now the flux could be changing either because B is changing, A is changing, or theta is changing. I'm going to write this out in the most general way first. I want the final flux, so the final value of the magnetic field, final value of the area, final value of the angle, minus the initial flux, the initial value of the magnetic field, the initial value of the area, the initial value of the angle. Okay? And then I'm just dividing that by the amount of time that change over which that change takes place, which is delta t. Now, that's sort of a general way to solve any problem like this. Let's now look at the specific problem. The only thing that's changing is the magnetic field. So I'm going to rewrite this as negative n. Notice that the A isn't changing, the angle isn't changing. The only thing that's changing is just the magnetic field. Okay? Now, in another problem, it might be the area that's changing, or it might be the angle that's changing. So to calculate my answer, I just have minus 200, that's the number of turns, that's what n represents. The area of my loop, pi r squared, so pi times 0.020 meters squared, times the cosine of the angle, Remember, this is the angle between A and B. In this case, B is straight in. Remember, the surface area vector is straight out. So that would be, excuse me, an angle of 180 degrees. And then the change in magnetic field, 1.75 minus 0.5. And I want to take that all and divide by 0.15 seconds. So if you work that out, we would get an induced voltage of 2.1 volts. By the way, if I told you the resistance of the coil, then obviously you could use Ohm's law to find the current. Let's look at another example. In this case, we have the same circular loop, but now the magnetic field is uniform. It's not changing. And we're told that the coil is going to rotate so that after 0.2 seconds, the coil is now parallel to the magnetic field. Okay? So in other words, we're going to go from having the magnetic field going into the loop to the loop turning so that now the surface area vector is in that direction. Okay? So notice that the surface area vector is straight out when we start. The surface area vector is now to the right when we end. And so the question is, first of all, what's the direction of the induced current? Well, hopefully you see that if the magnetic field is going in, as that loop turns, there's going to be less going in. So the loop wants to make magnetic field going in. So thumb towards the screen, the induced current would be clockwise. In terms of figuring out what the induced EMF is, again, we've said that the surface area vector is straight out to start, and the surface area vector at the end is to the right. Remember that B is in the whole time. So our initial theta is 180, and our final theta is 90. So this is an example where it is the angle that's changing. Again, the induced EMF is just going to be the absolute value of N delta phi over delta T. And now as I write that out, I'm going to take the N. I'm also going to keep the area and the magnetic field out in front because those aren't changing. Again, we're just always using the fact that flux is BA cosine theta. So the only thing that's changing is the cosine, going from cosine theta F as our final and subtracting cosine theta I. Again, dividing by the time delta T. So let's plug in the numbers. We've got number of coils is 200. We've got our magnetic field strength, which is 2 teslas. The area is just pi r squared, so 0.020 squared times pi. And now we have the thing that's actually changing. We've got the cosine of 90 degrees, that's our final angle, minus the cosine of 180 degrees, that's our initial angle. And now we've got to simply divide by how much time it takes for this change to occur, which was 0.20 seconds. If you calculate that, you should find that the average induced EMF was 2.5 volts during that time. So notice that we've looked at a problem now where the magnetic field changed. We've now looked at a problem where the angle changed. Let's look at a problem where the area changes. So in this diagram, the bar which completes the loop in a magnetic field is moving to the right with a velocity v. So first of all, this is an uninsulated piece of wire here, and this is uninsulated as well. So notice that the bar is moving to the right and it's making contact with the metal here and here so that we get an effective loop like that. So that's the loop that we're talking about. Now, you'll notice that as that bar moves to the right, effectively what's happening is the area of the loop is getting bigger. In this case, we're going to use the derivative form of Faraday's law. We only have one loop here, so we can put n is equal to 1. So we get negative d dt of the flux. But again, flux is BA cosine theta. So I want to take the derivative of BA cosine theta. All right, well, let's first figure out what theta is. Remember that the surface area vector always points out. So the surface area vector is straight out, but the magnetic field is also straight out. And therefore, the angle in this case is 0, or cosine theta is 1. Okay, so cosine theta just goes to 1. And now we want to think about what's changing, B or A. Well, it's the area that's changing. So B is a constant, and therefore I can take it out of the derivative. So I get minus B dA dt. But why is the area changing? It's not changing because this length is changing. It's changing because this length is changing. So I'm going to call that length x. And so I get negative b d lx dt. But again, the L isn't changing, so I get negative BL dx dt. But what is dx dt? Well, hopefully you remember that that's the definition of velocity. And so what we end up with in this problem is that the induced EMF is equal to negative BLV. And that kind of makes sense. The faster the bar is moving, the more the area is changing per second, so the bigger the induced EMF. If the bar is not moving at all, there is no induced EMF. Let's look at one more conceptual example. The problem says the current in the wire is increasing. What's the direction of the induced current in the coil? All right, so first we've got to use right-hand rule number 2. And we've got to put our thumb in the direction of the current. So, put your thumb this way. And then notice that if your fingers are above the wire, they're pointing out. And if your fingers are below the wire, they're pointing in. So that the magnetic field being created by that wire is in. Now, that's not enough yet to figure out the direction of the current in this loop. Because remember, it's all about change. What we're told here is that the current in the wire, in this wire, is increasing. So that means that there's more and more magnetic field going into the loop. So what does the loop want to do? It wants to make magnetic field coming out. So use right-hand rule number 3. Point your thumb out at you and notice that your fingers are going counterclockwise. Okay. I definitely want you to understand this problem for the final and notice that there's some ways that I could change it. What if instead I had changed this word to constant? What's the answer now? Well, hopefully what you've said is that the answer would now be no current. Because remember, if the magnetic field is constant going into a loop, no current is generated in the loop because there's no change. Notice that if instead I change this word to decreasing, well, now there's less and less magnetic field going in. And so what does the loop want to do? It wants to make magnetic field going in. And so now I'd point my thumb towards the screen and I would get an answer of clockwise. Let's look at the most important application of Faraday's law, and that is in the AC generator. So other than nuclear or, well, I take it back. Other than solar power, basically all power that we use in this country is generated this way. It's generated by taking a loop of wire and turning it in a magnetic field. Now, generally that's done by heating up water, generating steam, and having the steam turn a fan blade or turbine that is connected to the generator. So this is the way we generate electricity in almost everything other than solar panels. Well, let's look at how it works. Basically what we do is we take a magnetic field. Notice the magnetic field goes from north to south. That's important to remember. And what we do is we take that loop and we spin it in that magnetic field. So we have to put in mechanical or kinetic energy, and what we're going to get out is electrical energy. So notice that the only thing that's changing here is the angle between B and A. Also, what we're going to do is we're going to turn this at a particular frequency, and therefore we can rewrite theta in terms of the frequency. Remember, that would be 2 pi f times the time, or omega. Remember, omega is just angular frequency, 2 pi f. So what we now want to do is simply see, what do we get when we do this? Well, we get that the induced voltage is minus N. The B and the A can come out of the derivative because they're constant. And then we have the derivative of cosine omega t. Therefore, what we get, since the derivative of cosine is minus sine, we get NBA omega, we got to remember to use the chain rule, times the sine of omega t. And that's the voltage that comes out when you simply take a loop and turn it in a magnetic field. The thing that's important to understand about that is we've alluded to the fact that alternating current, the power that we get out of a wall outlet, is sinusoidal. It looks like a sine wave. And you might have thought that the power company has to go to some great lengths to produce a nice sine wave. But now we know the reason that AC power looks like that is that's simply what comes out. If you put a loop in a magnetic field and you spin it, we've just shown that the voltage will be a sine wave, where the magnitude of the voltage, the biggest it can ever be, is just N times B times A times omega. So different countries use different standards. Here in the US, we use a frequency of 60 hertz. Other countries use 50. It doesn't really matter too much. But that's how we generate electricity. We're simply taking a loop of wire and spinning it in a magnetic field. A DC motor, I just want to touch on briefly. By the way, motors and generators are the same device. It's simply, do you want to put in mechanical energy and get out electrical energy, in which case we call it a generator, or do you want to put in electrical energy and get out mechanical energy, in which case we call it a motor. So we'd already talked about a DC motor. A DC generator is the exact same thing. Again, the only thing that changes it from an AC generator is we have the split ring, as we talked about in a previous chapter. And because that flips the direction of the current each time, instead of getting a sine wave coming out, we simply get a flipped value for that second part of the sine wave, so that way the voltage is always positive. By the way, in a real DC generator or DC motor, instead of having just one set of coils in one plane, we have a bunch of other sets of coils as well. And so each of those sets of coils is generating or creating current independently, and they get added up so that the voltage that actually comes out of a real DC generator looks more like that. I want to talk about one last application, which I think is kind of interesting. We talked about how a speaker works in the previous chapter. A microphone is the same physical device as a speaker. It's simply a magnet and a coil of wire and a membrane. But obviously, the size of each of these objects is quite different. What we're doing with a microphone is we're trying to take sound waves coming in and convert them to an electrical signal. So what we do is we have a very thin membrane, so it has almost no inertia, so it can respond to sound waves very quickly, even a high frequency sound wave. And we attach a small coil of wire to that thin membrane. So now we suspend that membrane in a way that it can freely vibrate when a sound wave comes in. Well, as that membrane vibrates, the coil is basically moving in and out relative to this permanent magnet. And therefore, we get a current generated in that coil that is directly proportional to the vibrations that came in from the sound wave. And so we get an electrical representation of the sound wave. Now again, on the other end of this, when we want to turn that electrical signal back into a sound wave, now we put it through a speaker, which does the opposite. We put the current into the coil, therefore it experiences a force because of the magnet, and it now moves in and out and creates the sound wave again. The last thing that I wanted to mention here, because we're going to pick up on it in our last online class for the course, is that there is a way to write Faraday's law in a more general way. Remember that when we talked about electric potential difference or voltage or EMF, we know that that's related to the underlying electric field. And so I can replace the voltage there with E dot dr, as we talked about back in our chapter on electric potential. And we're going to spend a lot more time talking about this in our last online course. But what this is telling you is if there's a changing magnetic flux, not only does it produce a voltage, but in an underlying way, what's really going on is it's creating an electric field. And so that's the most general way to write Faraday's law. And by the way, that is another, and in fact our final, of Maxwell's equations. Okay? So we've seen Maxwell's equations are Gauss's law for magnetism, Ampere's law, and now Faraday's law. So this is number 4 of Maxwell's equations. And we'll put that all together in our last online class.